Hello everyone. So welcome to this course on circuit complexity theory. So this is a theoretical course where we will be studying Boolean functions and more specifically models for computing Boolean functions, namely circuits, and we'll try to study that for a function what is lower bound on the size and depth of circuits that can compute such functions. And we'll also look at other various types of circuits such as formula circuits which have certain bounded depth, circuits which are allowed to use only a restricted number of gates, and using these circuits, what can we say? I mean, what can we say about the size and depth of such circuits that compute a function? Okay. So broadly, this is going to be the agenda for this course. So to lay the groundwork for our discussion, okay, so let us try to understand a few things. So informally, okay, what is a Boolean function? So when we talk about a Boolean function, so a Boolean function is a function that takes Boolean values as input. Okay, so we talk about, so when we say Boolean, we think of the values as coming from the set 0 1. So that takes 0 1 as input. Okay, and in this course we'll only be looking at a specific type of Boolean function, namely functions that, let's say, go from a domain of size n to domain of size 0 1. Okay, so what we mean by these things we will clarify in a moment, but roughly this is what we mean when we talk about a Boolean function. Okay, so now next is, what do we mean by gates? Okay, so gates are a type of Boolean function that compute a very specific thing. Okay, so for example, we have gates like AND gate, we have OR gate, we have the NOT gate. We can also have other type of gates such as the parity gate. Okay, so the AND gate will output 1 if all of its inputs are 1. The OR gate outputs 1 if there exists some input which is 1. The NOT gate just takes one argument as its input, and it will output 1 if and only if its input is 0. And the parity gate outputs 1 if, let's say, that exactly one of its inputs are 1. Okay, so we can define, for example, if I look at the parity function and let's say we are looking at the parity in two variables, so we can define the parity of xy in terms of this truth table. So x and y can take values 0 0 or 0 1, 1 0 or 1 1. So the parity of x and y will be 0 if both x and y are 0, 1 if exactly one of x and y are 1, and again 0 if both x and y are 1 as well. So this is the parity function. These are some things that we know. So again, so these are just some examples of gates. There are, of course, you can construct gate for any Boolean function, and it is not necessary that a gate has to take just two inputs. You can have gates which can take arbitrary number of inputs as well. Okay. Okay. So now let us. So before we formalize things, before we get into the formal definition of all these things, let us just look at some motivation. Let us look at an example. In fact, we will look at this parity function only. Okay. Okay. So this is a function that is going to be very important for us. I mean, as we go uh, forward in this course, we will actually be studying this function in various contexts, and yeah, we'll get better understanding of this function. But how can I define parity of x and y in terms of, let's say, AND or NOR gate? So one way to define parity function in terms of AND or and NOT gates is parity of x and y is, so x or y and not of x and y. So what it is saying is that if, so suppose if both x and y are 0, then this part is 0, and if both x and y are 1, then this part is 0. So the function will be 0 if on these two cases, and if one of x and y are 1, then both these terms are 1, therefore the parity is 1. Now using this definition, we can actually get a graphical representation, which is actually what a circuit is. So we can represent this as follows. So I have AND, and so it takes x or y as input. I have a AND gate that is also taking x and y as input. I have a NOT gate, and then this is producing x parity y for us. Okay, so x and y, so this is producing x or y, this is producing x and y. Now this is giving us NOT of x and y, and then finally we have an AND of NOT of x and y together with x or y, exactly what we defined over here. Okay, so this is a circuit computing x parity y. Now, is this the only circuit for x parity y? The answer is no. I mean, there can be, in fact, one can give infinitely many number of circuits. I mean, one can have circuits with gates, with inputs which are actually redundant. I mean, of course, if the number of input bits are fixed, then the number of such circuits is not infinite, it is finite. But one can have lot of circuits. Okay, so another way of representing the same circuit is as follows. So it uses the same formulation. So I have AND, and I have OR over here, followed by x, y, and I have an AND over here. Once again I have x and y. Okay, so this is also another circuit computing x parity y. Now, what is the difference between these two circuits? Of course, the underlying graphical structure is different, but a more fundamental difference is that if you observe these two circuits, this circuit over here has the property that no node has out degree greater than 1. Okay, in fact, all of the nodes, so this is the output node, and all the nodes have out degree at most 1, whereas here you can see that these two nodes have out degree equal to 2. So if a circuit has out degree at most 1, it is also what is called as a formula. Okay, so also a formula. Okay, so now here I have defined the parity function for 2 bits. What about parity of n bits? Okay, so suppose if I want to define x1, x2 up to xn, what can we say about this? And basically, what is the parity of xn? So this is equal to 1. So again, it is defined in the natural manner. So basically, if an odd number of the bits are 1, then it will be 1 and it will be 0 otherwise. So it is equal to 1 if an odd number of the input bits are 1 and it is equal to 0 otherwise. Okay, so this is the natural way of extending the definition to arbitrary number of input variables. Now, how can I build a circuit for the generalized version? So, the generalized version one can see that so one way to define this is through an induction. So, how to build a circuit for this function. Okay, so the idea is you build the circuit inductively. What do we mean by that? So what we mean is that so suppose I have a circuit for x1 up to xn minus 1. So okay, let me put it this way. So x1 up to xn is the same as x1 up to xn minus 1 parity with xn. Okay. Now, suppose I already have a circuit for this. Okay, so let's say this gives me some circuit. Let me call it as Cn minus 1. Now, I build a circuit Cn. Let me call this as Cn, which takes the circuit for Cn minus 1. It takes the single variable xn and it builds a circuit using this and this. Okay. Now this is a circuit which has only some constant number of gates. So therefore I get a circuit of size Cn minus 1. So the size of Cn minus size of Cn one can show inductively, or what I mean is that I haven't defined size yet, but the number of gates in Cn is at most one can show it is 4n. Okay, so again this one can show by induction that for n minus 1 it is 4n minus 1. Now to go from n minus 1 to n, one needs to add at most 4 additional gates. So something similar to this, and this will give me a bound of 4n. Okay. Now this gives us a bound or an upper bound on the size of a circuit computing the parity function. What about, so here is a question, what about an upper bound on the formula size computing x1 up to xn. Okay. So if one tries to just generalize this argument, one will get a formula size of size exponential of size 2 to the power n. But can one do better than 2 to the power n? Okay, can one argue that for parity there is a formula whose size is sub exponential? Okay, something that is strictly better. Okay, so this is something for you to think about. Okay, so that is enough of motivation. So now let me get to some definitions. Okay. So a family of Boolean functions is a mapping f from 0 1 star to 0 1. Okay. It's a function from 0 1, so it takes a string and produces a output in 0 1. Okay, and the input can be any length. Okay, so the input of the function can be of any length, and n array Boolean function is a mapping, let me call it as f of n, from strings of length 0 1 to the power n to 0 1. Okay, so if the function takes inputs of a fixed length, we call it as a n array Boolean function. So now one can see that a family of Boolean function, a family of Boolean functions can be represented as a family of n array Boolean functions for n greater than or equal to 0. Okay, so in other words, we can represent f as f0, f1, and so on. Okay, so basically for each length I have a function of that, I have a n array Boolean function of that particular length. Okay, so now we get to the definition of circuit. Okay, so before defining circuit, I'll define one more thing. So that is a basis. So a basis omega is a set of Boolean functions. Okay, so okay, now let me define circuit. A Boolean circuit is a directed acyclic graph. So a Boolean circuit is a directed acyclic graph such that all nodes of in degree 0 are labeled by a variable xi or by the constants 0 or 1, all nodes of in degree greater than 0 are labeled by a function in omega. Okay, so this is also called okay, gate. There is a designated node of out degree 0 called the output gate. Okay. So yeah, so in this course usually we will look at circuits which have a single output gate. That is, basically we look at only Boolean functions, that is functions which output a either 0 or 1 only. So therefore there is a single output gate. Okay, so a Boolean circuit, okay, so a Boolean circuit over a basis sigma. So what is a Boolean circuit? So it's a directed acyclic graph where I have each input. So each node of in degree 0 is called an input node. So it can either be labeled with a constant 0 or 1, or it can be labeled by one of the variables that are present. All the nodes that have in degree greater than 0 are labeled by a function also called a gate belonging to sigma, and there is a designated node called the output gate, that is a node with out degree 0. Okay, so now note that once you have a Boolean circuit, it can take a fixed number of input variables. Okay, because it is a circuit which has a fixed number of nodes of in degree 0, and each node is labeled with a variable. So therefore it only can take a fixed number of input variables as its input. Okay, so therefore a circuit is essentially computing an n-array Boolean function. Okay, so suppose if a circuit has n variables as input, it is computing a n-array Boolean function. Okay. Okay. So now now we define what a formula is. So a Boolean formula is a circuit where every node has out degree at most 1. Okay, in other words, basically only the output node has out degree 0. Other than that, every node has out degree exactly 1. Okay, so it has a tree like structure. Okay. So that is what a Boolean formula is. the size of a Boolean circuit is the number of gates in the circuit. Okay, so usually we don't count the input nodes. So it is the number of nodes of in degree greater than 0 that are there in the circuit. That is what we refer to as the size of a Boolean circuit. So now, whenever we define a circuit, okay, it is with respect to a basis, that is, it is with respect to a set of functions which we allow to be the gates for that circuit. So now, what are some of the standard bases that we use? Okay, so firstly, we have examples of some standard basis. So basis is the plural for basis. So what are examples of some of the standard bases? So we have the De Morgan's basis, which is represented also as omega. It consists of the gate and, or, and not. Okay, we have the basis B2, which is essentially all Boolean functions on two variables. And how many Boolean functions do we have on two variables? So there are a total of 16 different functions. So the size of B2 is 16. So any gate can be any one of those 16 different functions. Another a very commonly used basis is the basis which has doesn't have a name. So we have the NOT gate, and then we have unbounded OR and unbounded AND. Okay. So basically we have OR gates that can take arbitrary number of inputs and AND gate that can take arbitrary number of inputs. The way they are defined is exactly the same, that is, an OR gate with an arbitrary number of inputs is 1 if at least one of its inputs, if at least one of its input is 1, and an AND gate with an arbitrary number of inputs is 1 if all of its inputs are 1. Okay. So these are some of the bases, but there are other interesting bases also that that one can study. Okay, so here is a couple of very simple results. So the first one is of course a fact. So there are a total of 2 to the power n functions over n inputs. Okay, so suppose if I consider a Boolean function going from 0 1 to the power n to 0 1, how many such functions are possible? Okay, how many different functions can I have that take an input string and produces a single bit as an answer? Okay, so first of all, note that the total number of inputs that are possible is 2 to the power n. Okay, if I have n input variables, each variable can take two different values as inputs. So there are a total of 2 to the power input, 2 to the power n inputs. Now each input can have two outputs. Okay, so for each input, either that input can be mapped to a 0 or that input can be mapped to a 1. Okay, so therefore there are a total of 2 to the power 2 to the power n different functions over n variables as input. Okay. Now when we have a circuit over n variables, okay, so now we can actually compare. Okay, so we can compare that. Okay, on one side I have this many functions, and on the other side how many circuits do I have that that can actually compute those functions. Okay, and then we can actually compare that. I mean, it allows us to give bounds on the size of circuit. Okay, so my size, I mean, my circuit should have size at least so much, so that it is able to compute each and every one of those 2 to the power n functions. Okay. So we next is we define the star size of a circuit as the number of gates not including the NOT gate. Okay. So if I count only the number of non-NOT gates in a circuit, that is what is called the star size of that circuit. Okay, so and often it is interesting to look at the star size, because one can often use standard techniques and bring down all the NOT gates to the input level. So what one is left with is only the non-NOT gates. Okay, so the star size is often a interesting parameter to look at. Okay, so here is the first result that we will see. Every Boolean formula has a circuit of star size at most n into 2 to the power n. Okay. So any Boolean formula. So we have a sorry, every Boolean, not formula, every Boolean function. So we take any of those 2 to the power n many Boolean functions over n bit input. So every Boolean function has a circuit of star size at most n into 2 to the power n. Okay. So again, to be more specific, every Boolean function on n variables has a circuit of star size this much. So how do we prove this? So the proof is actually quite simple. So we take the Boolean function and we look at the truth table of the Boolean function. So consider the truth table of the Boolean function. How many rows will there be in the truth table? So it will have 2 to the power n rows, and in each row basically the number of uh, columns that you would have is n columns. Okay, corresponding to each variable. So each row corresponds to each setting of the variable, and each column corresponds to a different variable. Now the value of the function can be thought of as taking an OR of all the rows, and inside a row it is basically taking an AND of all the what are known as literals. Okay, so whatever, so if a variable is set to 1 in a particular row, you take that variable in its positive form, and if a variable is set to 0 in a particular row of the truth table, you take the negation of the negation of that variable, so not of that variable. Okay, so therefore every row has, so okay, we consider what is known as a sum of product representation. So let me write this: sum of product representation of this function. Now in this representation, every row of the function is represented by n minus 1 AND gates. Okay, and so there are 2 to the power n times n minus 1 many AND gates, and then the way we combine all these products or all these AND are using OR gates. So we have a total of there are 2 to the power n OR gates. In fact, to be more specific, there are actually 2 to the power n minus 1 many OR gates, but that's okay. 2 to the power OR gates. So therefore the total number of gates is equal to 2 to the power n into n minus 1 plus 2 to the power n, which is equal to n times 2 to the power n. Okay, and we are of course not counting the NOT gate, so this is the star size. Okay, so any Boolean function n variables can be represented by a circuit having star size at most n into 2 to the power n. Okay. So this gives us an upper bound. Okay, so basically an upper bound on the circuit size. But note that this upper bound is actually quite non-trivial, I mean quite trivial to obtain. Okay, and this is a very large upper bound. Okay. Now what if I ask questions such as this, that if I, let's say, bound the size to be polynomial, what kind of Boolean functions are computable by circuits that have polynomial size, or what kind of functions cannot be computed by circuits that have polynomial size. Okay, so these questions become much more interesting. So as we go along this course, we will look at more and more such type of questions, and we'll also look at various types of circuits. So not just any arbitrary circuit, but circuits that have depths, circuit whose depth is bounded by something, circuit which allows a certain type of gates, and so on. Okay, so I'll stop here today. Thank you.